right now, you are listening to this audio because a metal box in a warehouse, likely thousands of miles away from you, is drawing exactly 300 watts of electrical power.
Right.
And if that box suddenly starts drawing, say, 400 watts, an alarm goes off.
Exactly.
But if it hits 1,700 watts, a physical breaker violently snaps open, the power is severed, and, well, this audio simply stops playing.
It's just gone.
Right. We treat the internet like this ethereal dimension where our photos and emails just kind of float in the ether. But the reality is loud. It's incredibly hot, and it's tethered to the ground by heavy copper cables.
It really is the ultimate industrial reality. I mean, if you were to walk onto the floor of a modern data center today, the first thing you'd notice isn't the data.
No, it's the noise, right.
Oh, absolutely.
Yeah.
It's the physical force required to maintain it all. You have the deafening roar of industrial cooling fans, the freezing temperatures in the cold aisles, and just this staggering amount of raw, high-voltage electricity coursing through overhead trays and underfloor conduits.
Yeah. And to pull back the curtain on how that chaotic physical reality is actually tamed, we are doing a deep dive into a very specific, incredibly detailed technical document today.
Yeah, we are.
Specifically, we have our hands on the draft user guide for Supermicro's SuperCloud Composer, or SEC Power Infrastructure Module. This is, let me check the notes, release 3.13.0, version 1.0, dated right now, August 2026.
And I realize that, sitting down to dissect a technical user manual for power infrastructure might seem, at first glance, a bit dry.
Just a little bit.
Right, but our mission for this deep dive is to decode this specific document because it fundamentally operates as the hidden nervous system of the modern data center.
Yeah.
We are looking at the literal interface where human administrators control the physics of the cloud.
Okay, let's unpack this, because this manual is absolutely not, a basic guide on how to plug in a monitor.
Yeah.
This document is the control panel for the internet itself. Our goal here is to uncover how systems administrators actually wield control over the massive, sometimes genuinely terrifying amounts of power running through thousands of server racks simultaneously.
And we need to start by establishing exactly what the SuperCloud Composer actually is.
Right.
SEC is this comprehensive software application designed to manage power distribution units. And in the industry, those are universally referred to as PDUs.
The TDUs, okay.
Right. And the software provides a centralized console, a single pane of glass, to use the industrial term, that allows an admin to track physical geographical locations, hardware assets, individual power outlets, and even tunnel directly into the specific web servers hosted on the power units themselves.
Which brings up the question, why should you, the person listening to this right now, care about a centralized console for power distribution units?
It's a fair question.
Because every time you swipe a credit card, every time you stream a 4K movie, or, I don't know, every time your hospital updates a medical record, that action relies entirely on the microscopic, precise management of electrical power described in this exact August 2026 document.
It's the foundation of everything.
If the systems detailed in this manual fail, your digital life just halts. So let's start at the absolute foundation. Before we get into the software, we really need to understand the hardware.
Yes.
We are looking at Section 1, the anatomy of a PDU.
So the manual defines a PDU fundamentally as a device for controlling electrical power in a data center.
Okay.
On a very basic level, it takes a massive high amperage power feed from the facility's main electrical panel and distributes it into multiple smaller outlets for individual servers.
Like a power strip.
Basically, yes. But the SEC application doesn't just treat all PDUs equally. It categorizes them into 4 highly distinct tiers, and that's based on their internal logic and capabilities.
Yeah, I saw that. The manual outlines this hardware spectrum that ranges from, honestly, totally dumb metal to highly sophisticated network devices.
Right.
The first tier is labeled the basic PDU. The text says it offers simple power distribution only. So I have to imagine this is effectively a heavy-duty version of that standard, $10 household power strip that you probably have stuffed behind your television right now.
That's a perfect analogy.
It just takes one plug from the wall and gives you 10 plugs for your gear, right?
Functionally, yeah, that is exactly what it is. It splits a 30 amp or 60 amp circuit into individual 15 or 20 amp receptacles.
Okay.
It has a physical circuit breaker to prevent a catastrophic fire, but it possesses absolutely no microprocessor.
So no brain.
No brain at all. It has no network card. It cannot report back to an administrator about how much power is flowing through it, nor can it be controlled remotely. It is a strictly physical pass-through.
Which honestly brings up a massive operational question for me. Yeah. If I'm a systems architect, right, and I'm spending hundreds of millions of dollars to build a state-of-the-art data center facility in 2026, why on earth would I ever provision a basic, completely dumb power strip?
It sounds counterintuitive.
It seems like a massive liability. Is it purely just a budget constraint, or is there a strategic argument for simplicity here? Like maybe if there's no software on the power strip, it can't crash or get hacked?
You are hitting on a major ongoing debate in infrastructure architecture.
Really?
Oh, yeah. It is a mix of capital expenditure because outfitting 10,000 racks with intelligent power units costs an astronomical amount of money and security footprint.
Okay, the security part makes sense.
Right, because a fully networked device is just another IP address on your management network. It is another piece of firmware that needs patching. It is literally another vector for a cyber attack.
Right, another door into the house.
Exactly. So some facility managers prefer their power delivery to be entirely isolated from their network architecture. They'd rather monitor power at the main facility breaker, not down at the rack level.
Wow. Okay. But if you do want that rack level visibility, you have to move up to the second tier, right? What the manual calls the metered PDU.
Yes, the metered tier.
And the manual states this unit displays current, voltage, and power usage.
Right. So the metered PDU introduces a localized brain. It usually has an LCD or LED screen right on the metal chassis.
Oh, like physically on the box.
Exactly. So a technician can physically walk down a freezing cold data center aisle, open the back door of a server rack, and look at a digital readout to see that, okay, this rack is pulling exactly 14 amps.
Very old school.
It is. Now, some metered units also have a basic network card that passively broadcasts those metrics back to a central server, and that allows for historical data logging. But, and this is key, the flow of power is still immutable from afar.
Meaning you can watch the power, but you can't touch it.
Precisely.
To touch it, you need the third tier, which the manual calls the switched PDU.
Yes.
This adds remote outlet control right on top of the monitoring. So now, a sysadmin sitting at a desk in London can selectively cut power to socket number 4 in a server rack located in a facility in Singapore.
And the operational leap here is just massive.
I bet.
Think about it. If a server operating system completely locks up and refuses to accept network commands, a technician no longer has to physically drive to the data center at 3 a.m. just to push a plastic power button.
Oh, that saves so much time.
Immense amounts of time and money. The switched PDU contains internal relays. The remote administrator commands the relay to open, which physically breaks the electrical circuit to that single server.
Wow.
And then they command it to close, forcing a hard physical hardware reboot.
And finally, perched at the very top of the hardware spectrum, we have the intelligent PDU. The manual describes these as fully networked, featuring continuous data logging and offering complete full-spectrum monitoring of every variable imaginable. And not just power, but environmental data too.
Yeah, intelligent units are essentially robust IoT computers that just happen to distribute electricity as their day job.
That's a great way to put it.
They calculate power factor, they monitor individual phase loads, and they literally serve as network hubs for external temperature and humidity sensors.
And the reason this spectrum is detailed so meticulously in the SuperCloud Composer Manual is that the SEC software has to act as like the universal translator for all of them.
Exactly. That's its primary job.
I noticed that in the text. The manual has this incredibly dense matrix mapping out supported PDU models and the specific features they unlock in the software interface.
It's a massive chart.
Yeah, it tracks whether the device is metered, switched, and crucially, whether it supports advanced features like cascading, threshold activation, and threshold edit.
A prime example from the text is the Raritan PX3 series.
Let me look at that, yeah.
The manual matrix checks every single box for the PX3. It does metering, it switches outlets, it allows you to daisy-chain devices together, and allows the SEC to actively rewrite the alarm thresholds on the device itself.
It's the fully loaded model.
Right. But then you contrast that with the supported server tech models. Specifically, the text mentions the C2W-W36TE and the C2WG-24TB.
Okay, looking at that chart now. So the server tech models give you the metering, they let you switch the outlets on and off. You can edit thresholds. But the manual explicitly notes a gap.
What is
They
it?
do not support cascading.
Right there. So the software has to dynamically disable UI elements based on that exact hardware limitation.
Because the hardware physically can't do it.
Exactly. And the complexity multiplies even more when you look at the massive lineup of Schneider Electric devices the manual supports.
I mean, the Schneider list takes up pages in this document.
It spans generations of hardware. You have the APDU 10350SM and the 2450SM, which are these flagship units with full functionality. But then the manual details much older units, like the AP8941 and APDU 9941. And according to the SEC compatibility matrix, those older models only support threshold activation.
Wait, meaning the software can turn the alarm feature on, but it can't granularly edit what the alarm limits actually are.
Correct. The limits are hard-coded into the unit itself.
Oh, wow.
And even newer hardware introduces quirks, like the manual proudly highlights the brand new EPDU line models, like the EPDU 2032 SMBO X100 and EPDU 2263 SMBO X100.
Yeah, they literally mark them with a new badge in the text.
They do, and they offer metered and switch capabilities and threshold editing, but they fundamentally lack cascading support.
Interesting.
The core challenge for the SuperCloud Composer software is seamless abstraction. An administrator using the SEC shouldn't have to remember if rack number 42 have a Raritan or a Schneider unit. They just need to know if they can turn the power off.
Okay, so that seamless abstraction relies heavily on how the software organizes this absolute chaos.
Yeah.
So we know the hardware exists. We have this vast spectrum of metal boxes distributing electricity, some with basic screens, some with complex IP networks.
Right.
The pressing question is, how does an operator actually find one specific metal box in a facility that contains tens of thousands of them?
It's a needle in a very large haystack.
Exactly. So this moves us out of the physical server aisle and into the digital interface of the software. Section 2, the command center.
So managing thousands of power units requires a remarkably rigid, unforgiving organizational structure.
You can't just wing it?
No, absolutely not. The SCC interface forces users to navigate through what it calls the data browser, which operates on a strict hierarchical tree view.
Okay, like a folder structure.
Very much so. An administrator cannot simply look at a massive, flat list of every power strip in the building. They have to traverse the physical architecture digitally.
Right.
They start at the POD level, which is a distinct physical cluster of racks. From the POD, they drill down into a specific group, and from the group, they drill down to the individual rack level.
It mimics the actual physical layout of the building perfectly.
Yes.
And the user manual is fascinatingly strict about how the UI behaves if you navigate to an area that hasn't been populated yet.
How so?
Well, it notes that if the PDU list you're looking at is entirely empty, the software immediately locks you out of making any configuration mistakes.
Oh, it disables the UI.
Yeah, all the operational function icons in the group bar become grayed out and disabled. If you hover your mouse over them, it just displays this leak tooltip message. No resource found.
See, that is a deliberate defensive design choice.
Defensive?
Yeah. The system is engineered to prevent a tired administrator from accidentally sending a power command to a null space or attempting to apply a configuration template to a rack that doesn't physically exist in the database yet.
Ah, that makes sense. It saves you from yourself.
Exactly. The only tools the UI leaves active in an empty list are the reload button to refresh the database query, the view or eye icon, and the search button.
And speaking of that, the manual goes into serious depth regarding that search protocol. The granularity available to the operator is staggering.
It has to be.
I mean, if you have an incident at 2:00 a.m., you aren't just typing server rack 5 into a search bar.
During an outage, speed and precision are paramount. Every second costs money. The filters allow administrators to search across highly specific database fields.
What kind of fields?
You can filter by the exact IP address of the unit, the PDU location string, the group name, the manufacturer, the precise product SKU, the serial number, and a very specific field called the cascading mode.
Let's talk about searching by product SKU or serial number for a second.
Sure.
If I'm an admin, why am I searching for a power strip by its serial number? That seems too specific.
Okay, imagine a scenario where a specific batch of Schneider Electric PDUs is recalled by the manufacturer due to, say, a faulty capacitor that poses a fire risk.
Oh, a hardware recall.
Exactly. The manufacturer gives you a list of affected serial numbers. You do not want to walk the floor of a 1,000,000 square foot facility, opening rack doors to check tiny little stickers.
No, that would take weeks.
Right. So you punch the serial numbers into the SCC search filter, and the software immediately illuminates exactly which racks and which pods contain the fire hazards.
That is incredible.
Or if a unit dies in the middle of the night, searching by the exact Singy C tells the on-call technician exactly which replacement model they need to pull from the hardware inventory room before they ever walk out onto the floor.
That makes perfect sense. It's inventory management tied directly to operational control.
Precisely.
But I want to zero in on that last search filter you mentioned, because the manual dedicates a significant amount of ink to explaining it. Cascading mode?
Yes, cascading.
The search filters allow you to look for units where cascading is set to on, off, or not supported. What exactly is a cascading chain physically? Like, what does that look like?
Well, if we connect this to the bigger picture of data center networking, we have to talk about cable management and port density.
Okay.
A standard server rack has a piece of networking gear at the very top called a top-of-rack switch. This switch might have, say, 48 ports to plug in servers.
Right.
If you have 2 intelligent PDUs in that rack and each one needs an Ethernet cable to communicate with the SCC software, you are burning 2 network ports just for power management.
So 2 ports per rack. And across 1,000 racks, that is 2,000 expensive switch ports dedicated purely to power strips.
Exactly. Not to mention 2,000 unique IP addresses pulled from your management network subnet, and 2,000 physical Ethernet cables that have to be meticulously run, labeled, and zip-tied.
That sounds like an infrastructure nightmare.
It is. Cascading is a hardware feature designed to solve this cable nightmare. It allows multiple PDUs to be daisy-chained together physically.
So they just share a single connection back to the main network.
Yes. They are linked and managed through a single primary network uplink. And the SuperCloud Composer manual provides a highly specific diagram to illustrate how the software interprets this physical chain.
I'm looking at that diagram now.
It shows a Schneider Electric APDU 10450ME acting in the primary cascading role, which the industry terms the master.
And physically plugged into that master unit, you have the downstream units, which the text refers to as the slave units.
Right.
The diagram in the manual specifically shows a different model. An APU 10450SM acting as a slave, and then another APDU 10450ME also acting as a slave, and they're all chained beneath that single master unit.
Architecturally, only the master unit is plugged into the top-of-rack network switch. The master unit holds the primary routable IP address.
Wait, just one IP address for all 3?
Just one. In the manual screenshot, it shows an IP of 172.31.3.38. The SCC software talks exclusively to that one IP address.
That's fascinating.
When the software needs to execute a command on the third power strip in the chain, it sends the command to the master, and the master delegates the protocol down the physical daisy chain to the correct slave unit.
Wow. How does the software display that relationship to the human operator? Because if they only see one IP, couldn't that be confusing?
Visually, the SCC interface completely understands and reflects this hardware hierarchy. When you look at the PDU list in the data browser, it dynamically indents the slave units beneath the master unit in the UI.
So it literally looks like a folder structure on a computer.
Precisely. It creates an immediate visual understanding of the blast radius.
Blast radius.
Yeah. The administrator knows instantly that if they see the master unit go offline, the indented slaves haven't necessarily lost power, but they have absolutely lost their management connection. Cascading drastically reduces IP address consumption and cable clutter while maintaining total visibility within the software.
Okay, so we've navigated the hierarchical tree, we've utilized the granular search filters, we've found our specific PDU, and we know exactly where it sits in a cascading chain.
Right.
We basically have our virtual hand on the digital power cord.
We do.
But a power outlet, no matter how intelligent or well-networked it is completely useless if we don't know what it is actually plugged into.
That is the big catch.
This leads us to what feels like the most critical vulnerability in the entire system: server power mapping.
It really is the hinge upon which the entire illusion of control rests.
How so?
You can have all the electrical data in the world, you can know exactly how many amps are flowing through an outlet, but if you do not know with absolute certainty which physical server is drawing that power, you are flying blind.
Yeah, that makes sense.
Managing power without a map is like knowing a patient's heart rate, but not knowing which hospital room they are in.
Oof, yeah.
The SCC tackles this monumental challenge through a feature it calls the system drawer list.
The manual spends a lot of time explaining how the SEC maps a physical rack's power distribution to a specific server chassis or drawer.
Yes.
And it doesn't just explain it theoretically, it provides a highly specific visual example of how intricate this mapping gets in a production environment.
It gets complicated quickly.
The text outlines a scenario involving a physical rack named AllRack1. Within that specific rack, the administrator has installed two separate PDUs, which the system labels as AllRack1B and AllRack1C.
It's important to pause and understand why there are two PDUs in one rack. This is standard redundancy.
Okay?
PDU-B is likely fed from power grid A, which is perhaps the municipal utility. PDU-C is likely fed from power grid B, which might be backed by the facility's on-site diesel generators.
So if a backhoe cuts the municipal power line down the street, grid A dies, PDU-B loses power, but PDU-C keeps the rack alive.
Exactly.
Yeah.
Total redundancy. Each of those PDUs has multiple physical outlets down its length, typically numbered sequentially. In the manual's example, they focus on outlets 1 through 7.
And the visual in the manual shows the digital mapping of this redundancy. It shows the power path from outlet number 4 on PDU-B and the power path from outlet number 4 on PDU-C, converging together and mapping directly into a single system drawer.
Right.
And the interface identifies that drawer as AllRack 1.4.
So the server drawer has two power supplies. The SCC software now understands that to physically power off server drawer, AllRack 1.4, it must simultaneously send a kill command to outlet 4 on PDU-B and outlet 4 on PDU-C.
Both of them.
Right. If the map only registers one of those connections, an administrator might attempt to reboot a frozen server, kill power to PDU-B, and watch in absolute frustration as the server continues running perfectly fine off PDU-C.
Here's where the scale of this problem gets genuinely wild to me.
Okay.
The manual outlines this mapping for a single drawer. But a modern data center rack might have 40 servers in it. A facility might have 1,000 racks.
Easily.
Mapping all of this manually in the user interface, like clicking and dragging virtual cables to virtual outlets for 40,000 servers, that would take a lifetime.
It would be impossible. And it would be impossible to maintain accurately, especially given the constant churn of hardware replacement and upgrades in a live environment.
Right. Things move around.
This is why the manual transitions immediately to discussing the ability to import and export the outlet config file.
Yes, you can export this massive configuration file out of the SEC as a standard Excel document to your local download location.
A simple spreadsheet.
This blew my mind.
Yeah.
You are literally using a Microsoft Excel spreadsheet to import the foundational power map of an entire data center.
It's all just cells and rows.
I'm thinking of this like a massive city planner mapping out the water lines for an entire metropolis. If the city planner assigns the wrong water main to the wrong hospital, the consequences are disastrous.
Absolutely.
Matching the exact outlet ID in a spreadsheet like string AA4 to the exact server drawer determines if that specific system lives or dies during a power event.
The city planner analogy is highly accurate because a desynced map is the absolute worst-case scenario for a systems administrator.
What happens when it desyncs?
Imagine a technician physically unplugs server 1 from outlet A and plugs it into outlet B, but fails to update the Excel spreadsheet.
Human error.
Right. Now, the software's reality diverges from physical reality. Weeks later, the administrator attempts to reboot a problematic email server plugged into outlet A. Because the map is wrong, they unknowingly send the reboot command to outlet B.
Oh, no.
And instantly, they hard crash a perfectly healthy database server.
And because the stakes of that desync are so unimaginably high, the user interface has incredibly strict, almost militant rules about how you handle these configuration files.
That has to lock you down.
The text explicitly points out a strict UI rule during the import process. Users are physically prevented from selecting individual checkboxes or even multiple checkboxes to import or export mapping files for specific isolated drawers.
Right, you cannot update the map piecemeal.
If you select just 3 checkboxes out of 50 and click the gear icon to import a new map for just those 3 servers, a dark gray caution box instantly pops up in the center of the screen and blocks the action.
And what does it say?
The manual quotes the exact error message. Selection is prohibited for this option.
The software architecture enforces a macro-level view of reality. It forces the administrator to import or export the configuration for the entire list of drawers within that rack or group all at once.
It's all or nothing.
Exactly. It absolutely prevents a scenario where a user might accidentally upload a partial map. That would leave half the rack mapped to a new configuration and half the rack mapped to a legacy configuration.
Which would be chaos.
Complete chaos.
Yeah.
By forcing a holistic update, the SCC guarantees that the database's understanding of the physical rack is uniformly applied, preventing disastrous miscalculations of power loads and routing.
Okay, so the city planner has double-checked their work. The Excel file is imported flawlessly. The digital map is perfectly synchronized with the physical cables on the data center floor.
The map is good.
Once everything is perfectly mapped, the user now has ultimate granular control. What actually happens when an administrator needs to interact with the raw electricity?
This is where things get serious.
Right. This transitions us out of configuration and into the outlet list features. Section 4. Playing God.
The outlet list is the operational heart of the SuperCloud Composer. This is where the actual physical manipulation of alternating current occurs.
Okay.
And because flipping a power switch on a production server is such a volatile action, the console provides an incredible depth of telemetry before you ever touch a button.
For every single individual outlet in the facility, the console tracks a constantly updating stream of metrics.
That's a lot of data.
It really is. It tracks the basic state, which is just a binary indication of whether the relay is open or closed, on or off.
Right.
But then it gets into the physics. It tracks the total energy consumed by that specific plug over time, measured in kilowatt hours. It tracks the live current draw, measured in amps. It tracks the real-time power consumption, measured in watts.
And it doesn't just present these numbers in a vacuum. The software categorizes the electrical load contextually.
What do you mean by contextually?
Well, it tracks peak power, logging the highest spike that outlet has ever seen. It categorizes the current state into bands: power low load, power near overload, and power overload.
Oh, so it tells you what the numbers mean.
Exactly. The SCC is constantly evaluating the electrical stress on that single specific socket against the known physical limits of the hardware.
And based on all of that telemetry, the user can access the action menu to perform actual power management. But the manual points out a really interesting software engineering hurdle here.
Oh, the vendor differences.
Yeah. The actions available in the drop-down menu actually change depending on the physical hardware manufacturer of the PDU.
This goes back to the software acting as a universal translator. Different hardware vendors build different API endpoints and use different command terminologies in their internal firmware.
And the manual explicitly shows this. If the software detects you are managing a Schneider Electric PDU, the drop-down menu gives you 3 clear options: on, off, reboot.
Standard terminology.
But if the map indicates you are looking at a Raritan PDU, the menu options morph to on, off, cycle.
Cycle.
Yeah. To a human, reboot and cycle mean effectively the exact same thing. But the SCC has to translate the human intent into the specific proprietary syntax that the Raritan hardware requires to trigger the physical relay.
It is abstracting the vendor complexity away from the user, but regardless of whether the button says reboot or cycle, the physical action initiated by that command is what demands our attention.
I became really fixated on this exact point in the text because it highlights the sheer power the user holds.
It's a lot of power.
When an administrator selects an outlet, or multiple outlets, and chooses reboot from the dropdown, the command doesn't just execute. A mandatory pop-up warning takes over the screen.
It halts everything.
It asks, would you like to perform a power reboot sequence for all PDU outlets within the list? And below that terrifying question is a simple blue button that says, yes.
You are fixated on it because it represents a massive breach of the standard digital protocol.
Exactly. Isn't it terrifying that with 2 casual mouse clicks, selecting a checkbox and clicking, someone sitting at a laptop in a coffee shop halfway across the world could initiate a hard reboot on a live server rack hosting, I don't know, millions of banking transactions?
What's fascinating here from a systems architecture perspective is that this software is deliberately designed to introduce friction.
Friction.
Yes. The SEC requires these explicit mandatory pop-up warnings because a remote reboot command sent to a PDU is not a soft, graceful shutdown of the operating system.
Right. It's not clicking shutdown in Windows.
No. When you command an OS to shut down, it flushes its cache, it safely writes temporary memory to the hard drive, it gracefully closes database connections, and then it sends an ACPI signal to the motherboard to power off safely.
It packs its bags before leaving.
Exactly. But when you click Reboot in the SuperCloud Composer, you are bypassing the operating system entirely. You are commanding the PDU to physically snap open a mechanical relay. The flow of electricity halts instantly. The hard drives lose power mid-spin. The memory evaporates.
It is quite literally pulling the power cord out of the wall, but doing it digitally.
Precisely. And then, a few seconds later, the relay snaps closed again, and the massive inrush current slams back into the server's power supplies.
That sounds aggressive.
It is an incredibly violent electrical event. It introduces a massive risk of data corruption, specifically to databases that were in the middle of a write operation. It is an absolute undeniable last resort, used only when a server is completely frozen, unresponsive to network traffic, and just cannot be salvaged by any other means.
And because that manual intervention, that physical power cycle, is so dangerous to data integrity, the entire architecture of the system is designed to prevent you from ever needing to push that button in the first place.
It wants to keep you away from it.
The software wants to warn you before the server freezes, before the power spikes, which brings us directly to the concept of power thresholds. Section 5, Living on the Edge.
The core philosophy of enterprise infrastructure management is that you never want to be surprised. You want the system to tap you on the shoulder and alert you to an anomaly long before that anomaly melts a motherboard or trips a facility breaker.
Right.
But before an administrator can even configure these early warning systems, the manual points out a very specific foundational technical hurdle regarding how the software and the hardware communicate.
Right. The manual dictates that the SEC uses a protocol called SNMP to talk to the power units. But it can't just use any version. It strictly requires SNMP version 3.
Version 3 is critical.
The text specifically calls out that older firmware on the PDUs might not support this encrypted communication. It gives a rigid example. An APC Schneider APDU 10350 SMSM physically requires a specific firmware package named in the text as APDU 10kv2.8.2.zip to be manually installed on the unit before SNMPv3 is supported and thresholds can be managed.
Understanding why SNMPv3 is a hard requirement illuminates the security posture of the modern data center.
How so?
Well, SNMP, or Simple Network Management Protocol, is how network devices share telemetry. But versions 1 and 2 of this protocol sent their authentication credentials called community strings in absolute plain text across the network.
So if hacker breaches the management network.
If a bad actor gets access to the management VLAN, they could simply sniff the network traffic, read the plain text password, and then use that password to send malicious shutdown commands to every single power strip in the building,
Wow.
instantly turning off the entire data center.
That's a nightmare scenario.
It really is. So SNMP version 3 introduces robust cryptographic security. It encrypts the payload and requires cryptographic authentication.
Okay, that makes sense.
The SuperCloud Composer mandates V3 because sending power threshold commands over an unencrypted channel is just an unacceptable security risk. You can't just buy the hardware, you have to ensure its digital brain is modernized enough to securely handle the SEC's complex instructions.
Okay, so assuming the hardware is patched and secure, the administrator navigates to the Edit Active Power Threshold Settings window. This is where the guardrails are built.
And the software provides 4 distinct threshold parameters that the user can define, all measured precisely in watts.
4 levels.
Yes. You have the lower critical limit, the lower warning limit, the upper warning limit, and the upper critical limit.
The user interface design here is quite clever for managing scale. At the top of the threshold window, the manual points out 2 distinct radio buttons.
Oh, at the macro settings.
Yeah, you can choose Set Threshold separately, which allows you to meticulously define these 4 exact limits for one individual, highly unique server outlet.
For a specific machine.
Right. Or you can select Set Identical Threshold, which acts as a macro, applying the exact same limits to a whole batch of selected outlets simultaneously.
Which is a massive operational time saver if you are provisioning a homogeneous server rack where every single 1U server is identical in hardware and workload.
Just click, drag, and apply.
Exactly. But let's look at the actual physics of why setting these specific thresholds matters so deeply. The manual provides a very clear numerical example in its screenshots.
Right.
It shows a configuration where the upper warning threshold is set at 400 watts, and the upper critical threshold is set significantly higher at 1700 watts.
Okay, let's walk through a scenario based on those numbers. I have a server hosting a web application. Normally, under standard load, it's pulling a steady 300 watts.
Okay.
It's well below the warning limits. But suddenly, a piece of code gets caught in an infinite loop or a massive spike in user traffic hits. The CPU usage maxes out to 100%, the internal cooling fans spin up to maximum RPM, and the physical power draw spikes to 450 watts.
So it crossed the line.
Right. It has now crossed the 400-watt upper warning limit. What exactly happens in the system?
The localized microprocessor inside the PDU detects that the draw has exceeded the defined parameter. It immediately generates an SNMP trap, an encrypted alert message, and fires it across the network to the SuperCloud Composer software.
And the SEC sees it.
Right. Within the SEC dashboard, an indicator linked to that specific rack likely turns yellow. The administrator is now instantly aware of a thermal or computational anomaly.
But the server is still running. The power hasn't been cut.
Exactly. The warning buys the administrator time to investigate. They can log into the server, see the infinite code loop, and restart the specific application service, dropping the power draw back to 300 watts without ever impacting the physical electricity.
That's the ideal scenario.
But let's say the spike isn't a software bug. Let's say it's a catastrophic hardware failure.
Uh-oh.
The power supply in the server shorts out, and the draw begins to climb exponentially. It hits 800 watts, 1200 watts. Finally, it hits 1800 watts, violently crossing the upper critical limit of 1700 W defined in the manual.
Now the dashboard in the SEC turns red. The system is screaming for immediate intervention.
But here is the crucial physical reality of the situation.
Yeah.
The actual physical circuit breaker built into the PDU hardware, or the breaker on the facility wall panel, might be rated for 20 amps, which translates roughly to 2400 watts.
Wait, so the physical breaker hasn't tripped yet?
Precisely. By allowing the software to set the upper critical limit artificially lower at 1700 W, the SuperCloud Composer is generating screaming high-priority alerts to the human administrators before the rigid physics of the bimetallic strip inside the circuit breaker forces it to snap open.
It's a buffer zone.
Exactly. If that physical breaker trips, it doesn't just cut power to the one failing server, it cuts power to the entire circuit, taking down every single server plugged into that bank.
It takes down the collateral damage.
By utilizing these software thresholds, the SEC shifts the entire philosophy of data center power management. It moves the facility from a reactive posture where technicians run around blindly responding to tripped breakers in the dark to a highly proactive posture.
That is a huge shift.
The software provides the human beings a window of time to migrate virtual machines off the failing hardware, throttle CPU speeds, or cleanly shut down non-essential services before the laws of physics dictate a catastrophic rack-wide blackout.
It's a brilliant abstraction of physical limits into manageable software data. But power management isn't just about the isolated flow of electrons through a copper wire in a vacuum.
Not at all.
It is deeply tied to the physical environment. As power flows, electrical resistance creates heat. As heat rises, the atmosphere of the room fundamentally changes, which leads us to the final and arguably most complex piece of the SuperCloud Composer puzzle, the pulse of the room. Section 6, Sensors, Analytics, and the Broader Power Grid.
When you move beyond the outlet list and navigate into the sensor reading view of the software, you realize that the PDU is acting as much more than an intelligent power strip.
What else is it doing?
It serves as an environmental sentinel. The very first thing the UI presents are the device status charts.
Right, these charts track the historical data we discussed earlier, energy in kilowatt hours over time, and raw power in kilowatts over time. But the text explicitly notes a very strict color-coded gauge design for these visualizations.
A threshold arc.
Yes. They utilize a threshold arc. Green equals normal operation, yellow equals a warning state, and red equals a critical state.
In an emergency scenario, an administrator does not have time to mentally calculate if 1600 watts is a dangerous number for a specific rack configuration. The color-coded arc provides instant visual triage.
Keep it simple.
Right. Is the dial in the green? Move on. Is it in the red? Focus here immediately. Below those overarching charts, the UI delves into deep electrical engineering telemetry with the phase and bank status.
The manual notes that it monitors phase layouts, specifically calling out configurations like L3N and L2N. We need to translate this. What does that actually mean for the power grid?
Well, massive data centers do not run on the standard single-phase power that feeds your residential home.
Okay.
They run on three-phase power, which delivers 3 distinct alternating currents continuously, allowing for massive power delivery. L3N refers to tracking the voltage between line 3 and the neutral wire. L2N is line 2 to neutral.
Why does the software need to track the individual lines, though?
Because of a concept called phase balancing. If an administrator plugs too many heavy draw servers into the physical outlets wired to line 1 and leaves line 2 and line 3 empty, the electrical draw becomes dangerously lopsided.
Like a boat tipping over.
That's exactly it. This imbalance creates immense heat on the neutral wire, which can literally cause the power cables under the floor to melt and catch fire.
Oh, wow.
The SEC software monitors these phases in real time, allowing the administrator to visually ensure that the power load is perfectly distributed across all three electrical phases, preventing a localized meltdown.
And right next to that incredibly dense, heavy electrical phase data, the interface presents the environment status. The software tracks the environment temperature of the rack, toggleable between Celsius and Fahrenheit, and crucially, the environment humidity as a percentage.
This localized sensor data feeds directly into the macro-level power grid console module within the broader SuperCloud Composer ecosystem.
The big picture.
Right. The manual notes that this grid console isn't just looking at a single rack's temperature. It is configured to ingest and analyze massive facility-wide metrics.
It lists a barrage of acronyms here. It analyzes LNP, it calculates PUE, it aggregates emitter data, and it tracks GPU flex metrics.
Those are critical numbers.
Let's break those down because they seem to represent the economic heartbeat of the data center.
They absolutely do. Let's start with PUE, or Power Usage Effectiveness. This is the holy grail metric for data center economics.
The Holy Grail.
Yes. It is a ratio that compares the total amount of power entering the building to the amount of power actually used by the computing equipment.
So if a facility draws 2 megawatts total and 1 megawatt goes to the servers, the PUE is 2.0.
Exactly. Meaning you're spending an equal amount of electricity just running the cooling systems, the lights, and overcoming transmission loss as you're running the actual computers.
That sounds expensive.
It's highly inefficient. Modern data centers strive for a PUE closer to 1.1 or 1.2. The SEC software constantly aggregates the e-meter data from the main facility feeds and compares it to the micro-level PUE data from the PDUs to calculate this real-time efficiency score.
And what about LMP and GPU flex?
LMP stands for Locational Marginal Pricing.
Wow.
It ties the software directly into the volatile, real-time pricing of the regional electrical grid outside the building.
Oh, like utility rates.
Right. If a heat wave hits a city and the cost of utility power skyrockets at 3:00 p.m., the SEC software knows about it.
And GPU flex.
GPU flex relates to the modern era of artificial intelligence workloads. AI servers using massive GPU clusters have incredibly dynamic, volatile power draws compared to traditional web servers.
They fluctuate more.
Drastically. They might pull 500 watts while idle and suddenly spike to 3,000 watts when a massive machine learning training run begins. The software has to flex and allocate power grid resources dynamically to handle these massive, sudden tidal waves of electrical demand without tripping the main facility breakers.
What really stood out to me in looking at this sensor reading interface is the visual hierarchy.
How they arrange it.
Yeah. The document, and the software UI it describes, treats a subtle drop in room humidity with the exact same level of visual importance and urgency as a massive electrical power surge on line 3.
It does.
To an outsider, that seems disproportionate. Why is humidity equal to voltage?
Because to a sensitive server motherboard, an environmental failure is just as immediately lethal as an electrical failure.
Lethal.
The microclimate inside a data center aisle must be tightly controlled. If the cooling systems fail and the temperature spikes, the physical processors will hit their thermal limits and initiate an emergency self-shutdown to prevent the silicon from literally melting.
So the server dies just as surely as if the power was cut?
Exactly.
Humidity.
Humidity is even more insidious. If the air in the data center becomes too dry, if the relative humidity drops below a critical threshold, the environment becomes highly conducive to electrostatic discharge.
Static electricity.
Right. A technician simply walking across the floor to inspect a rack can build up a static charge. A single invisible static spark jumping from a finger to a server chassis can instantly fry millions of dollars of networking equipment.
That is terrifying.
By presenting temperature, humidity, and phase voltage on the exact same dashboard, the SCC software unifies the electrical physics with the atmospheric physics.
It takes the raw, violent flow of electricity and the physical air of the room and fuses them into one single pane of glass. It recognizes that you fundamentally cannot manage data center power without simultaneously managing the physical atmosphere that the power exists within.
It is a masterful orchestration of environmental and electrical reality.
Okay, let's take a breath and recap the incredible journey we've just taken through this August 2026 technical manual.
It's been a lot.
We started by looking at a seemingly simple piece of metal distributing power, the PDU. And through the lens of the SuperCloud Composer software, we discovered a massive, intricate digital ecosystem.
The nervous system,
We saw how it maps physical servers to redundant electrical outlets with the strict precision of a city planner, how it monitors live three-phase voltage to prevent fires, how it allows administrators to set proactive threshold warnings to beat the physics of circuit breakers, and how it controls the absolute heartbeat of the facility, outlet by individual outlet, all while constantly checking if the air in the room is too dry.
It is a staggering level of control, abstraction, and orchestration required just to keep the lights on.
So the next time you are sitting on your couch and you experience a brief, frustrating moment of internet lag or a critical online service goes down for unscheduled maintenance, remember this deep dive.
Remember the physical reality.
Remember that the cloud isn't magic. Because somewhere in the world, in a freezing cold, deafeningly loud room, there is likely an administrator staring at an SEC dashboard, looking at an upper critical warning arc turning bright red, desperately trying to balance a spiking GPU power load before a physical breaker violently snaps open.
They are the human beings managing the very heavy, very physical weight of our supposedly weightless digital world.
Which leaves me with a final lingering thought, directly inspired by a small, almost throwaway reminder tucked away in this manual.
Oh, the disclaimer.
Yes, the text explicitly warns users. Due to variations in PDU manufacturer implementations, features such as thresholds mappings, outlet ID naming, outlet type, and sensor alert data may differ.
It reads like a very standard boilerplate technical disclaimer.
It does. But think about the massive structural implications of that sentence. If the entire internet relies on this much physical electrical infrastructure to exist, and that infrastructure is managed by a patchwork of completely different, fiercely competing vendors like Schneider Electric, Raritan, ServerTech, who are all building different metal boxes, running entirely different proprietary firmware, and translating their electrical data completely differently into this one SuperCloud composer software.
It makes you wonder.
How fragile is the illusion of a seamless, perfectly unified cloud?
It really forces you to realize that if the foundation of our digital lives is a constant, ongoing translation between competing hardware standards, the cloud isn't a monolith at all. It is a very precarious, incredibly well-orchestrated, and highly vulnerable mosaic.
A precarious mosaic of heavy metal, high-voltage electricity, and translated code. Thank you for joining us on this deep dive into the hidden physical infrastructure of our digital lives. As always, stay insanely curious.